question before we talk about Lab7? Also, just a reminder, today is the deadline for lab practical. Okay, so if you haven't done the lab practical, you should finish them today. Okay. Any questions?
Yeah.
Yeah.
So for the lab practical take-home portion, do we just use the symbols for the first question that
No,
were shown from the video?
no, I'm not sure the video, but it's not the symbol. Okay, I can tell is what I can tell is not the symbol. For example, the wattmeter is not the like just a circle with the V. So that's not right. You need to go to the lab menu to find what the model looks like. Okay, it's not just simply a symbol.
And the lab manual, is that from any particular experiment, or how do we find it?
You should, if you remember, like we talk about the wattmeter or current meter, which is ammeter, at the first couple lab or first 3 lab. So you should go those labs. Yeah. Any other questions? Okay, if now let's talk about Lab7. So, Lab7 is inductors and capacitor. Okay. First of all, the capacitor. Basically, if you put two metal plate like together, but put some insulator in between, so that's a capacitor. Okay, so here is physically the equation for the capacitor. So C is the capacitance, D is the distance between two metal plate, and A is the area of the metal plate. And then this is permittivity, and then this is relative permittivity. You can find the number here. So different insulator have different relative permittivity. Okay, so this is how you physically calculate the capacitance. And then the inductor. And the inductor basically is just a metal coil. So something looks like this could make a inductor. Okay, so this is a equation for the inductor. If you done the pre-lab, you should use this equation in pre-lab. Okay. Just make sure you understand what's the meaning of each parameter in here. Okay. Like there are two R indicate different radians. Okay. Then another thing I want to mention is circuit relationship. Okay, so remember, if in the resistor, when you put two resistor in series, okay, the total resistance is just two resistor value plus together. Okay, if they are in parallel, you need to use the parallel equation to calculate the total capacitance. And similarly, for capacitor and inductor, they calculate in a similar way. But remember, for capacitor, when the two capacitor in parallel, the total capacitance is they plus together. Okay, C1 plus C2, that's the total capacitance. But when two capacitor in series, okay, then you need to use the same equation as when the resistor in parallel. Okay, so you need to use this equation. And similarly for inductor, the inductor is same way as resistor calculation. Okay. And the last thing here is voltage divider. Okay, you can still use the voltage, build the voltage divider circuit by inductor or capacitor or inductor. So you can find the equation over here. Okay, this equation is pretty similar with the resistor one, but for the capacitor voltage divider equation, if you check carefully, the numerator is different. Okay, it's the top component right here, which is C2, is at the top of the equation. Okay, make sure you remember this for the voltage division circuit. Okay, and here is this example is a very good example for the capacitance and inductance calculation. Okay, make sure you go through this example before either the pre-lab and also the lab experiments. Right, let's talk about the experiment really quick. Okay, so today you have 3 tasks. Okay, should be not too hard. The first one and the second one is similar. You're going to build the figure 7.6 and then measure the capacitance and the inductance. Okay. So okay, before I talk about the experiments, there's a quick thing I want to mention is the impedance. Okay, so the impedance of a resistor is simply a resistance, but the impedance for the capacitor is 1 divided by j omega c. Okay, j is an imaginary number, and omega is equal to 2 pi f. F is the frequency. And for the impedance of the inductor is j omega L. Omega still the 2 pi f, which is f is frequency. You probably don't need those equations right here, but just make sure you have a general idea. The impedance of the capacitor and inductor is related to the frequency. Okay, you will need those equations in the later class, so make sure you remember those 2 equations. Okay, so then let's talk about task 1 and task 2. Okay, so as I mentioned, task 1, task 2, you're going to build this circuit right here, which is figure 7.6. Okay, and the R sense is already given. I think for the task 1 is 1 k ohm. Okay, and then you put the 10 nanofarad capacitor at the DOT, which is device under test. Okay, after you build this circuit, okay, and then you use the oscilloscope to measure the voltage. Okay, you need to measure. You can use one of the channel measure at input. Okay, if you use channel 1, and you can use channel 1 as a measure of input, and use channel 2 to measure the output. Okay, so channel 2, the output which is a voltage across the DOT. In the task 1 is a voltage across capacitor. In the task 2 is a voltage across the inductor. Okay, this circuit diagram here is for the benchtop equipment. Okay, because the benchtop equipment can only take the single-ended measurement. Since you're using AD2 here, okay, so you don't have to use a mass function to measure the voltage cross R sense. Okay, why we need voltage cross R sense is because if you take this equation, okay, to calculate the capacitance right here, you need to know what's the current cross capacitance and also what's the voltage cross capacitance. The voltage is just the channel 2 here, okay, and the current cross capacitance. Okay, what you need to do is you want to calculate the current cross the resistor. Why is that? Because the 2 components, they are in series. Okay, so the current cross the resistor is same with what the current across the capacitor. So how you can get the current across the resistor is you can measure the voltage across the resistor at here, and you divide by the R sense, then you get the current, right? So if you're using AD2, you don't need to use the mass function right here. What you can do is use channel 1 plus at here, okay? And put channel 1 minus right here, 1 minus, okay? Then the AD2 can take a differential measurement. Then the waveform on your channel 1 of in the waveform software, that's the voltage cross R sense. Then you just divide by the R sense value, then you can get the equation. Okay, so after you get two equation, okay, so one equation is IC, equation is VC. Okay, then you can start the calculation. Okay, remember those two, the IC and the VC, those are two equations because they are those are two waveforms. Okay, so then you can start to do the calculation. So the easier way here is you choose the whatever as the derivative as sine wave. Okay, then another one will be cosine wave. Because if you make everything correctly, you should see two signal have 19-degree phase shift. So if you make one of them to be sine wave, then another one will be cosine wave. Okay, the reason why you put the derivative, you do the derivative calculation for sine wave is the sine wave derivative is just the cosine wave. Okay, if you do the derivative of cosine wave, you have a minus sign, so that's makes the calculation a little bit more difficult. Then after you get the calculation done, you should have a you should have the cosine wave at the left side of your equation and also a cosine wave at right side of your equation. Then you can cancel them, and then at the end you should only have a value for capacitor. Okay. Then for the task 2, the calculation process is pretty much similar. But remember, you put the derivative as sine wave. Okay. Make sure the voltage is at the left side of your equation. All right, I think that's all for task 1 and task 2. I will show you how to do the calculation or how to find the value of the capacitor and the inductor later. It's actually already in the right space. Okay, if you check start here, okay, I think probably in lab 1. Okay, it should be, I can show you later. There is a document tell you how to find the capacitor and resistor, capacitor and inductor in your lab kit. And I can show you what the capacitor looks like soon. Okay, any question for task 1 and task 2? Okay. Make sure when you are doing those two tasks, include when you take a screenshot, the screenshot should looks something like this. Okay, make sure when you get this two waveform for task 1, task 2, take a screenshot of those two waveform. Okay, you'll need the screenshot in the write-up. All right, then task 3 is pretty simple. You've done something similar before, which is a voltage divider circuit. Okay, so you've done the voltage divider, which is just two resistors in series. In here, you just change the resistor to capacitor right here. Okay. Right, then for the function generator, you will use the AC signal with those two parameters and use the oscilloscope to check the input and output. Okay, so basically the circuit is something looks like this. Okay, you use channel 1 to check the input, channel 2 to check the output. And at the end of the circuit should be channel 1 and channel 2, and also the ground. Okay, make sure you connect the ground at the end of the circuit. Okay, make sure you don't forget the ground. I forgot to include the ground here, but make sure at the end of the circuit. Okay, so that's the ground. Ground is the black pin at the 82. Right, then in step number 4, you take a screenshot for the input and output. Okay, make sure you include the measurement of the input out and output. At least include the VPP or the amplitude. All right, and then you just follow the instruction here. Okay, the step number 6 right here. First of all, you need to sweep the frequency from 1 Hz to 1 kHz. Okay, so remember when you have low frequency, okay, so 1 Hz, let's say 1 Hz or 5 Hz or 10 Hz. Okay, when you detect the low frequency signal, what you need to do is you need the roll mode. Okay, and then when you increase the frequency, you come back to the normal mode for the measurement. And another thing here is the attenuation ratio. Okay, so what's the attenuation ratio? It's just V out amplitude divide V in amplitude. That's the attenuation ratio. Okay. Then in last step, you just change the function generator to DC and see does it still work like a voltage divider. Okay, I think that's all for the experiments for today. Any questions? Okay, the last thing I want to mention besides the capacitor and inductor is the red hat. Okay, so for the red hat, at least start from today, okay, you need to include the circuit diagram of your experiment. Okay, so for example, the circuit diagram right here is a good example of the task 1 and task 2. Okay, then this is circuit diagram for task 3. Okay, make sure you include them in the red hat. Okay, so that's how show how like you do understand how to build the circuit. Okay. All right. Any questions? Okay. If there's no,
I
yeah.
I have a question about the pre-lab
Okay.
because the pre-lab is the due date is extended, but it seems that we have all the values, so I'm not sure why it extended. I just to make sure I do it right, but
It's
because it
extended because
extended,
the
maybe
reading wasn't
you
available.
mean
So if you wanted to do the reading before you did the pre-lab, it's available for you now.
oh okay.
Oh, I see. It is your question. The pre-lab time is okay. I see. Yeah, it's not extended. I think it's just a accident. The pre-lab for
No,
Lab7.
I did extend the pre-lab
Oh, okay. Oh,
7th.
I
That was
see.
just for the reading. Since the reading wasn't available, if you would like to do the reading
Okay,
before you do the pre-lab, it is available to you now.
okay, I see. All right. Any other questions? There's no question. Give me 1 second. I can find some picture for the capacitor. Okay, so those are some quick picture I found online for the capacitor and what the capacitor looks like in the lab kit. Okay, so you should have some of this in your lab kit. Okay, you should either have something looks like this or something looks like this, and probably something looks like this. All right. So for something looks like this one, the large one, you should directly able to see the capacitor value right here. Okay, they already label what's the capacitance here. So for example, this one is 1000 micro. Okay. Okay. By the way, make sure you understand like the difference from what's the meaning micro the nano. Okay, macro is 10 to the minus 6. Nano is 10 to the minus 9. Okay, and then next one is pico. Pico is 10 to the minus 12. Okay, make sure you don't forget that when you do the calculation. And then for the other two capacitor right here, you need to read the number. Okay. Okay, so for example, this one is 104 and this one is 222. Okay, so there should be a document on the course website tell you how to read the capacitor value, and then if, for example, if you have 3 digit number, and then you can start to do the calculation of the capacitor value. Okay, yeah, check this document definitely. And then for the inductor, 1 second. Ideally in your, not ideally, in your lab kit, there should be only one inductor, which is 1 million Henry. And I can show you what it looks like. Okay, the inductor in your lab kit should be something looks like this. Okay. So that's the inductor of the in your lab kit. And I think if for the small value of the inductor, that's, I mean, the capacitor, that doesn't matter. But if you are using, you see some of the capacitor, the two leads, okay, which is this two thing right here, those lines are different. Okay, always the longer side is the positive side. Okay, which means when you build your circuit, the longer side will be at this side. Okay, and this is the shorter side. Okay. Okay, that's how you treat the polarity of the capacitor and the inductor. I think for some small value of the capacitor, they don't have the polarity, but for some larger value of the capacitor, make sure the polarity is correct. Okay. Okay, any question about this? All right. If not, you can start the experiment. Just a reminder again, today is the deadline for the lab practical. And also I will open the breakout room. Okay, there are a couple questions. Okay, so first one is what's the RS in the figure 7.6? Okay, I forgot to mention that. Let me share my screen. Okay, yeah, good question. Here, if you you check the circuit right here, there is RS. Just ignore about this RX. Okay, just short the circuit here. So the RS, if you're using the benchtop equipment, the function generator itself have a 15 ohm internal resistance. But since you're using AD2, there is no internal resistance of the function generator. Just ignore about RS, just short to the C1. Okay. And I saw there is another question. Okay, so another question is for the capacitor. Okay, there's a code 2A103G. Okay, so what you need is 103. Okay, so that's the 3-digit number you will need to use. Okay, so you can just use the document I showed before. Okay, use this document to do the calculation. Okay, and another way I usually do is just Google it. 103 cap code. So if you see here, 103 is just 10 nano. Okay. Okay, so there is a question about like what's the difference between the differential probe and the LC scoop probe. So LC scoop probe have two kind of probe actually. So first one is a single-ended, and the second one is differential. So for the differential, what it mean is okay, let me share my screen. So for the differential one, okay, so what you can do is you can, when you measure the voltage of a component that's not connected to the ground. Okay, so for example, this RSense is not connected to ground because the ground is right here. Right. So if you have a differential probe, okay, you can put your probe, let's say 1 plus at here, and the 1 minus at here. Okay, so the probe can directly measure the voltage difference at this node and this node. Okay, so that's if you have a differential probe, you can do this. But if you don't have a differential probe, okay, let's say if you only have a single-ended probe. So for example, in this circuit diagram, what you need to do to measure the voltage across the R sense is you need to put your 1 plus right here, and your 1 minus can only connect to the ground. So that's the ground. This is the ground. Then what you need to do is you need another probe at here, which is, let's say, call it 2 plus. and then you need the mass function to subtract those two proofs to get the voltage cross our sense. Okay. So that's a difference from single-ended and differential. The differential one is easier for this kind of measurement. Okay, you can just use one channel of the proof. For the differential, if you only have a single-ended proof, you need two proof at this 2 point, and then to use the mass function to get the differential value.